Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here at my virtual classroom. Step on aside, and we're going to be dealing with some stuff in Integrated Math 1, solving exponential equations. Now, this is something where you have the variable up in the exponent, and this isn't just necessarily Integrated Math 1, it could be for IM2 or IM3, but for the current skill that I'd be teaching for my students, this is what we'd actually be looking at here, where we're trying to get that x. Normally, when you take Integrated Math 3, you would be doing something like this for a brief moment in time before you move into logarithms, trying to solve them when you can't do what we're going to do here, which is doing what's called changing base, or at least matching bases together. I have a worksheet for you guys with this one. There's a PDF of, I believe, 24 questions. If you check the description section down below, you can follow along with me or copy it down on binder paper. Just take a look at it. You'll see what's there. I'm also going to attach something called a power table, and I'll show you what that looks like as well in just a moment, because a lot of these I want you to try and do without a calculator if you do it. So check it out. It's going to be this sheet right here. It says skill number 19. Ignore that. But solving exponential equations, it goes 1 through 12 on the first page, and then 13 through 24 on the second page. And I'm going to do all of them. I'm going to speed up more as I go, in the sense that if you hear something more than once, I'd like to, hammer through it. But there are some new things that'll be hit over time. And although some problems may begin more introductory, there are some other problems that throw in some nice tricks along the way, some curveballs that, just be prepared. It's not necessarily the last question is the hardest. It could be near there, and we hit more fractions later, I guess, but just be ready for anything. Be ready for anything. Now, I'm going to show you what a power table is as well as we go. It is this thing right here. It's just a reference to raising numbers to certain powers. I do everything 1 through 12 in 15 and 16, at least for the squares, some of the cubes, some more fourths. I initially filled this completely out, like 16 to the 12th power, and the number's just too massive, obviously, right? That'd be somewhere in the quadrillions or something really huge. So I only did ones that were more common. I think one that's going to come up, though, is 11 cubed, so I'll keep it in mind like this. The whole gist of this table, guys, is you're going to reference this and try and search up with these numbers here what power you're raising a certain base to get these numbers. And you'll see what I mean when we do them. I'll point to in the video a couple times, but if I know the number after that, I'm just going to kind of keep moving forward. Okay, so solve each equation. We're going to start here straight up with number 1. Now, I'll write a property up at top in a moment. Here's the end goal. Obviously solve for x, but the end goal in solving for x is to get these exponents equal to each other by getting the same base on both sides of the equation. And in order to start that, you have to first get this base by itself, this 2 to the x power. Now it says 3 times 2 to the x power. I can't multiply the 3 with 2. Order of operations says exponent first, multiplication second. So I got to get this 3 out of the way on this side of the equation. I'm going to divide both sides by 3, like so. Divide by 3, and you get 16 on this side. You have 2 to the x on this side. Now I do not divide both sides by 2. I don't get x equals 8 for my answer. 2 to the 8th power is not 16. 2 to the 8th power is 256. It's 2 times 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 2. 8 2's multiplied. That is not the answer. You do need to find out 2 to what power gives you 16, and technically, since x is just that value, that'll give you the answer. But I want to go more into what you're going to need in the future for this. So my goal is to rewrite this with the same base on both sides. I promise you, if you do that more often, it's going to help you. So 2 to what power is 16? Well, we can try this. 2 times 2 is 4. Times 2 is 8, times 2 is 16. It'll be 4. If you use the power table, here's how you'd look at it. Refer to 2 as your base, find 16 in it, and discover what power that is going to be. So base is 2, 16 is the ultimate value, 4 is the exponent. This is 2 to the 4th power. So 2 to the 4th power equals 2 to the x power. Now that the bases equal each other, you're just going to set the exponents equal to each other. If 2 to some power equals 2 to some power, those some powers have to be the same, as long as those 2's are the same. So 4 equals x, better yet written as x equals 4. You can double check it. Plug in 3 times 2 to the 4th in your calculator. You should get 48. I'm going to move on to number 2. 64 equals 4 to the x power. This one already has the exponent by itself. The exponent term by itself. Nothing to multiply or whatever to both sides. So I just got to rewrite this 64 as 4 to some power. This, once again, if I refer to the power table, you use 4 as base. Find 64 in it and discover that that is 4 cubed that gets you there. So 64 is rewritten as 4 to the 3rd, and here's 4 to the x. And generally the exponent, I take back what I said. The first 4 problems, the x is on the right side of the equation, so oh well. But now that I have, I was going to say generally it's on the left side, but we can rewrite it on that side. 4 to the third equals 4 to the x. The 3 must equal x, or x equals 3. That's right. That's the value. What for? What power is 64? The third. Number 3, 83 equals 3 to the x power plus 2. This 2, again, doesn't add with the 3 as it's raised to the x. Get this 2 over to the other side of the equation. This time I'm going to subtract 2 from both sides because that's the inverse of addition. And now I have 81 over here and 3 to the x there. Once again, I got to find 3 to what power is 81. Why don't you take my word for it this time or check with the power table? What do you think? 3 to what power is 81? We can check with fingers. 3, 9, 27, 81. 3 to the fourth. So 3 to the fourth equals 3 to the x. Therefore, x equals, I'm going to go straight to that part, x equals 4. Y'all. Now, the first 3 problems already only had x in the exponent itself, and so that made it a lot easier to get to that final answer. Number 4 actually doesn't show that. So let's move on to number 4 and see what's going on. 25 equals 5 to the 4x power. Now, there's a 4 up there that doesn't change our process in what we're going to try and do, which is match bases. See, the first 3 problems, you're probably looking like, why don't I just write 4 as the answer if I find out it's 2 to the 4th? Why do I have to write this step? I'd argue that this is a kind of problem that can start getting into why you might want to do it. 25 is 5 squared, 5 to the second power. And you have 5 to the 4x here. Your goal is to get those bases matched. They do. Now we set the exponents equal to each other, but it does not give me the answer for x. 2 equals 4x. I still have to now solve for x algebraically. This isn't the only problem where we're going to have to do it. So you divide both sides by 4. 2/4 reduces to 1/2. By the way, get used to reducing some fractions. Even on this very sheet, I imagine there's going to be more fraction reduction. Maybe. I did them with notes for my students, so maybe. I haven't done this sheet before. I've seen it from some of my students, but I haven't done it, so we'll see. But yeah, x equals 1/2. 0.5, that's the value that goes there, because half of 4 is 2, and 5 squared is 25. All right, let's move on to number 5. Now, number 5 is a little bit trickier. 4 to what power is 32? My first step I said that I want to try and do is get this exponent term by itself. I have, and it's on the left side of the equation. That's fun. However, if we go to the power table and we try and look, 4 to what power is 32? Oh, it's in between some numbers here. Yup, it's in between the 16 and 64. It's not on here. So what's the answer? Don't make any guesses. We're going to be using some stuff in here. Oh, by the way, I didn't write a property on top I was going to write. Let me go to this first, because I want to write another property after this. If b to the x equals b to the y power, then x equals y. This is the equality of bases property. If you have bases that match and are the same, set the exponents equal to each other and solve. That's what we're doing here. The other property I want to write is this, ultimately based on what we do. Maybe we can't use 4 as our base. So what we're going to do is find another one that is a base that has powers of both 4 and 32. So let's go back and hunt in here. 4 didn't work. Let's try and find a smaller one. Did this have 4 and 32? No. Does this have 4? Yes. Base of 2, powers of 2 can get us a 4, and it can get us a 32. So we want to rewrite both bases here instead. Well, I want to rewrite 4 as 2 squared. And I'm going to do it here in parentheses to indicate that this is still the 4 that's being raised to the x power. 2 squared is to the x power. 32, if you check this, this is 2 to the 5th power right there. So this is 2 to the 5th. My goal is to match bases. This is one of the better problems than ever to really hit that home. I need to match bases. Now my bases aren't truly at match. This is still 2 squared. That's my base because it's raised to another power. It's kind of like a power to a power. And this is where I wanted to write that other property. If you have a power raised to another power, something in here, not literally the power itself, but something there, this ultimately leads to the exponents multiplying. And I don't think I need to get or want to get too deep into the why of the matter, but your exponents will end up multiplying together. So this 2, and this x will end up multiplying. And 2 times x is 2x. I can do this without parentheses now. 2 to the 2x power equals 2 to the 5th. I have now properly matched my bases. They are actually now the same. And now I can set these equal and solve. 2x equals 5. Divide both sides by 2. I will get x equals 5 halves. Improper fractions are fine. That's 2.5 as well, 2.5. But improper fraction is great. And that's the final answer. This goes back to, Mr. Robinson, how do I solve this problem? Match the bases. I'm not saying you could therefore get the answer, but if you try and think in any other way than matching bases, you're going to have a hell of a time trying to figure out what to do. I'm going to tell you that. Now number 6 is a little bit easier again. I can subtract 4 from both sides to begin with. Take my word for it. I'm subtracting 4, and I get 6 to the x power. 6 to what power is 216? Check the power table. It's going to be a 3. 6 cubed. Again, match the bases, and then therefore x equals 3. But I'll tell you what. I'm asking you to match base, for especially for problems like this. If you start to recognize, and I think on the second page I'm going to do this if they're easy. If you start to recognize that all you're doing is raising to a very simple integer power to get there, I think I'm comfortable getting to that final answer. But if we have a tricky bit where we have to figure out what to do based off that, and using more work will help you, do it. All right, number 7, 10 to the 2a power equals, I think that's 1 million. That's a 1 followed by 6 zeros. If I put the commas there, that might help you a little bit. 1 million. Now, as far as matching bases, I think 10 would be an ideal base for this. You multiply numbers of 10, amounts of 10, and you're going to get something eventually near a million. It's just going to basically add a 0 at the end of everything. 10 times 10 is 100, times 10 is 1,000, etc. So I need to rewrite this as 10 to some power. So on the left side, I'll do 10 to the 2a power equals 10 to the blank. Now you might be wondering, let's go to the power table and look at it. Well, in the power table, I stopped short at just 1,000. I didn't write 10,000 and all that. I didn't keep going because I would have ran out of room. This kind of helps tell you how to look at the power table. But here's what it also says. To continue increasing powers of 10, just add another 0 to the end of the number. The number of zeros is equal to the power of the value. I'm going to say that again. The number of zeros is equal to the power of the value. 10 to the second power has 2 zeros. 10 to the third power has 3 zeros. I have a 1 with 6 zeros following it. That's 10 to the 6th power. 1 million is 10 to the 6th power. So it doesn't show up in the table, but count the number of zeros and you can work that out that way. Okay, the bases match. Set the exponents equal to each other. 2a equals 6. Divide both sides by 2. A equals 3. 10 to the 2 times 3, 10 to the 6th is indeed 1 million. Okay, we'll deal with number 8. Now this suddenly just exploded into something significantly trickier, and I almost want to kind of move this 8 over a little bit to write something else I need to write. I have a fraction base and a fraction result. Even after multiplying by 4, I still have a fraction result. This is a z, by the way. I don't know if you can tell. It's not a 2 and it's not anything else. That's a z. What do I do? Okay, same thing applies as before. Get this by itself. Get this by itself. A 4 is multiplying by that. You might say let's divide both sides by 4. Okay, how do you divide a fraction by 4? There's a way to do it, but here's a better way to do it. Dividing by a fraction is the same as multiplying by that number's reciprocal. Reciprocal is where you take the fraction and flip it on its head. 4 means 4 divided by 1, right? If I flip that, that becomes 1 divided by 4. I'm not saying flip this. I'm saying multiply by the flipped version of that, 1/4. 1/4 means literally 1 divided by 4. We are still dividing by 4, but we're giving it a different appearance. Doesn't matter as much for this side, but it does matter for this side. Because how do I divide with fractions? You multiply by its reciprocal. And how do you multiply fractions? Straight across. 4 times 1, 9 times 4. But even better, you know how this is actually dividing? 4 is dividing by that 4 there. I can do 4 over 4, which is 1. Even get rid of those as I get rid of these, of course. 1 over 1 is 1 as well. And I'm left with 1/9 on that side. And this isn't the only problem I'll do this. So as I keep saying those kinds, hopefully it'll make sense as I keep going on. I think we have others like that. So 1/9 is here. Okay. Now another property in play is when a fraction is raised to an exponent. So if I take some sort of fraction and raise it to an exponent, that's equivalent to raising both parts of the fraction to that exponent. With that in mind, 1/3 to the z power equals 1/9. That means if I raise 1 to, that's the equivalent of doing 1 to the z power and 3 to the z power. So if that remains on top here, 1 to the z power must be 1. I got to find what value of z will get me 1 when I raise 1 to the power. And it can be anything. Look at this column here. 1 squared is 1, 1 cubed is 1, 1/4. Because you just keep multiplying by 1. It doesn't change. So which answer is it? Well, you have to remember, it's not just 1 you have to pay attention to. It's the 3 to the z power as well. That would get you 9. So 3 to what power is 9? 3 to the second power is 9. And guess what? 1 squared is 1. What's nice about the fractions is you get to find a thing that agrees with both of them. It needs to work with both. Otherwise, you did wrong math, or you need to reduce the fraction more, or they built a bad problem. But with this one, it should work out just fine. I need to rewrite 1/9 as 1/3 to the second power. 1/3 squared is 1 squared over 3 squared, which is 1/9. And now my bases match. Therefore, z equals 2. It's more important than ever that I make my z look like this because my 2 can look just like a z. Let me get a hit of water here while you absorb that. And we're going to start number 9. Okay. Number 9 just has an added step to something like you would have seen on number 1 or on number 6. Not necessarily trickier. It does have some negatives involved, but we'll take care of them. -2 times this plus 3 is -69. Now, this could look a little bothersome. Let me write this right next to it. -2x plus 3 equals -69. Let's say this was the problem. I just took 6 to the x and I turned it into x. Some people might say, I don't know how to do this, but I'll say, do you know how to do this? Let's see. What would you do first? Oh, subtract 3 from both sides. Yeah, I'd subtract 3 from both sides. Let's do the same thing here. Remember, I'm treating this like an x. I'm just 6 to the x, single variable. I want to get this by itself just like I want to get this by itself. So let's do that. Subtract 3 from both sides. -2 times 6 to the x equals -72. No difference. Now what do? Divide by -2. Yeah, divide by -2. Boom. Right? This was -3, by the way. Boop, do, 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 do. So here, divide by -2. That would be 6 to the x equals 36. I'm just going straight to that. I'm not actually solving for x over there. Point is, you want to get this thing by itself. Doesn't matter what it is. Just treat it like its own unknown. I'm not doing anything with it until it's by itself. I couldn't care less that it's a 6 or a 20 or a b. Get it by itself. It's after that that you start looking at it and saying, what's my base? Can I raise it to a power to get 36? What is that power? This time, let's save a step. 6 to the second power is 36. Therefore, this x has got to be 2. I'm skipping the matching base step in between because I don't feel it's really needed for that problem if I know what the number's going to be. Okay, let's go to number 10. 125 equals 25 to the x power. I don't have 25 in the power table, but I'm going to tell you right now, 25 to the second power is 625. This is already past it. So there's no power of 25 that gets me 125. This problem is going to be a lot like number 5. With 4 to the x equals 32. Let's find another number, smaller, in its place, that when you raise it to some powers, I could get 25 or 125. That's going to be 5. 5 squared is 25. 5 cubed is 125. Let's do that one. 125 is 5 to the third power. 25 is 5 to the second power. Remember, this is in parentheses, technically, as it's still raised to the x. It's still 25 to the x, but this property will now allow me to multiply these exponents together. So 5 to the third equals 5 to the 2x power. Boom, like that. Now I can set the exponents equal, and it's not a straight up solving thing, but now I can solve by dividing both sides by 2, divide both sides by 2, and I get 3 over 2. 1.5, if you will. That's the answer. Okay, let's go to number 11. It's another fraction one. The fraction is by itself, and I have 2 different ways to look at this. The exact way that it's written and a reduced fraction version. Let's start with the exact way that it's written right now. I did do a problem like this on number 8. Once we got there, we're raising both 2 to the x and 10 to that same x to get 8 over 1,000. So really think of it like 2 to what power is 8, and is 10 to that same power 1,000, or the other way around. 2 to the third power is 8. Does 10 to the third equal 1,000? It does. So straight up already, you could go straight from here and say, hey, x equals 3, right? That's the number that gets you there. 2 cubed equals 8. 10 cubed equals 1,000. Look, there's nothing wrong with what we did. It works. It's right. Nothing to reduce. This is the answer, 3. I don't have to reduce a fraction here. But let's look at a reduced fraction form as well if you want to go into that. You look at 8 over 1,000, you think it can divide by 2, it can divide by 4, and it can divide by 8. You divide top and bottom by 8, reduce this fraction, you get 1 over 125 if you divide them by 8. Now, if I looked at this off the bat right here, I'm just going to point this out for a moment. If I did this right here, you'd say, well, 2 to what power gives me 1? Well, that answer is 0. We're going to hopefully get in some of those. But 10 to what power is 125? Is it 10 to the 0 power? No, 10 to the 0 power would also be 1. I don't know what I raised 10 to get 125. Mr. Robinson, what do I do from here? Well, here's the problem. You reduced one fraction without reducing the other. 2/10 is inside this exponent and can reduce as a fraction as well by dividing top and bottom by 2. You don't write 2/10. 2 divided by 2 is 1. 10 divided by 2 is 5. You get 1/5. 1/5 the x is 1 over 125. Does this work? Yeah. 1 to any power is 1, but 5 to the third is 125, so 1 cubed is 1 works. This is still, once again, x equals 3. 1 cubed equals 1. 5 cubed equals 125, and you could have gotten it that way as well. It's your choice. Your choice. All right, those are two different ways to do that fraction problem. Number 12. Number 12 is already taken care of when it comes to getting the exponent term by itself. There are actually two of them in matching bases. They both have variables in them, but you're well on your way. If you, for any other reason you want to know why you match bases, it's because if I give you a problem with match bases, I want you to know what to do with them. The bases are the same, set the exponents equal. 2b equals b plus 5. Boom. Now do a little more algebra. B's on both sides of the equation. I'm going to subtract b from both sides like that. B minus b is 0. 2b minus b is b, and b equals 5. That's the answer. See, this would be 2 times 5 is 10, and 5 plus 5 is 10. 6 to the 10th equals 6 to the 10th. I don't even need to know what 6 to the 10th power is. My power table definitely doesn't, and I don't. I just know that I get the same answer with that b. Okay, we're halfway home, maybe even more so. Depends on the problem type. Let's take a look. Number 13, 3 to the negative 3n equals 3 to the negative 3n. This is one of the problems that most students would struggle in. It's so obvious that we have so much trouble with it. Look, ignore the fact that it's the same thing on both sides right here. Just look at the fact that you have matching bases. We have matching bases. Let's set the exponents equal. Negative 3n equals negative 3n. Okay, students still struggle in this part. They're like, what do I do? Well, what did we do on the last problem? Look at the last problem here. I had b's on both sides of the equation. And what did I do? I moved the b's to one side. I subtracted b to both sides, and then I solved for b. So let's do that. I have n's on both sides of the equation. Let's move them to one side. Let's take this negative 3n and add it over. Now, do never say something cancels out. Canceling out is not the right way you say something. What is negative 3n plus 3n? Don't say nothing. It is 0. Negative 3n plus 3n is 0. Negative 3n plus 3n is 0. And 0 equals 0. What did we say? I'm not going to get deep in this. This is something where I have other videos that always say this. If the variables cancel, I just said the word cancel. If the variables are gone from the equation and the left side equals the right side in a true statement, which this does, you have an all real numbers case for single variable equations. All real numbers. What does that mean? It means I could substitute anything, any number in the world to this equation, and I will get a correct answer because you have the same thing on both sides. Don't just say n equals 0 is the answer. Don't say n equals 1. Don't say n equals 20. Any of them work. Plug in 15. 3 to the negative 45 power equals 3 to the negative 45 power. I don't know what it is, but they're the same. And that's what this is here. Maybe you could have confirmed that, or like you could have concluded that from the beginning. It's up to you. I like to really hit home when the variables are gone in the equation and the left side equals the right side. We can make that statement. Okay, let's go to number 14. 3 to the negative 2x equals 81. I believe we already saw that 3 to the 4th was 81. So let's rewrite that as 3 to the 4th power. The bases match. Set the exponents equal to each other. Divide both sides by negative 2. You get x equals negative 2. Don't take my word for it. Double check, plug it in, see if it works. That's an example of a problem that goes pretty quickly after we've seen other ones like it. Okay, number 15, the bases match. Once again, let's set the exponents equal to each other. Negative r equals 1 minus 2r. Let's get the r's on one side of the equation. I tend to get them positive, so I'd like to add 2r to both sides like that. Negative 1r plus 2r is 1r. Let me just write r, is r. And there's a 1 still on this side. And that's it, r equals 1. Pretty fast, pretty good. Okay, number 16. You have variables on both sides alongside these bases here. I think you probably know that 81 to the second power is not going to be 243. That's going to be pretty big. I don't know what it is, but it's pretty big. Somewhere in 6,000s, I think, apparently. There must be a smaller base for these two. I'm curious to look at 9. 81's there, but 243 is passed. So it's not 9. Then I'm really curious. You can go back and I'm really curious to look at 3. And 3 seems to be it. It has 81. It has 243. 81. Oh, we already knew 81 from the last problem, but 3 to the 4th power, or the second to last problem, and 3 to the 5th power here. So 243 is 3 to the 5th. However, that also has an n up there. So this is 3 to the 5th to the n. 81 is 3 to the 4th, and that's still raised to the n plus 1. It's probably one of the harder problems on here for several reasons. Discovering that and still going forward. The next tricky bit, remember these multiply, so this is 3 to the 5 times n, 3 to the 5n power. On this side here, this one is a little tricky because here's what's going to happen. 4 is going to multiply with n plus 1, but it's not just going to multiply with n. It's going to multiply with n plus 1. It's a quantity. You're going to distribute this thing. I can save a moment and say this. It's 4 times n plus 1. So I'll distribute literally later with that. But that's what you do. It's not just 4 times n, or 4, because otherwise how do you make that choice? It's not just the first number. I could write 1 first. But now I got to distribute that, right? I mean, just look, set the exponents equal to each other now that the bases match. But you really got to recognize that. Another reason why this problem could be made harder as a result of that. So 5n equals, distribute this, 4n plus 4. And now I can subtract 4n from both sides. 5n minus 4n is 1n, and n equals 4. So apparently 243 to the 4th power is the same thing as 81 to the 5th power, 4 plus 1 power. Okay. Number 17, matching basis of 6. Let's set the exponents equal to each other. 2a equals, not 2a, 3a. Very much like a previous problem, some students would struggle and say, what do I do here? Do I divide by this? But no, get your variables on one side of the equation. I like to make mine positive. I'm going to subtract 2a from both sides. Why not? Subtract 2a, subtract 2a. 2a minus 2a does not cancel. 2a minus 2a is 0. 3a minus 2a is 1a. 0 equals a, or a equals 0. That is the answer. What can I raise 6 to a power of that has the same variable in a single term? Apparently 0. 6 to the 0 equals 6 to the 0. That is it in bit. That's all, folks. You're done. Stick a fork in ya. All right. Sorry about that. Let's keep moving. Number 18. Oh, that's a big number. I'm going to add 3 to both sides. Boom. Plus 3 plus 3. We got that. I got a negative exponent up here. And this is 15625. Just 3 more than that. Plus 3 plus 3. Boom. I got it. Unfortunately, and as I'm checking here, you know, maybe we're not using this number. I might have used this other number in one of my different examples. But 5 to the, I think it's to the 6th power. So 5 to the 5th is 3125. And 5 to the 6th is, I believe, 15625. That looks right. So it's 5 to the 6th power there. This is one where you might have to use the calculator, take a look at it, see how it works. And it does happen to work on that one. Still have a few more problems to go. So that is, once again, 5 to the, I said 6th? Yes. 5 to the 6th power like that. Bases match, set the exponents equal. Divide both sides by negative 2. You get x equals negative 3. That is a 3. Okay, number 19. I got a lot of fraction business here, and it's a 1/3 in front that's multiplying by this. Once again, you could say divide by 1/3, right? But that doesn't really help what we're doing with fraction and fraction. Multiply by its reciprocal. I think you're going to be much better off in life when it comes to that. The reciprocal of 1/3 is 3 over 1, or 3. Multiply by 3 over 1, if you will. They're gone because they become 1 times that thing. And now I have 9 times 3 over 125. Does 3... I don't think so. I don't think 3... If 3 reduced with 125, then so would 9. So I'm going to legit multiply 9 with 3 and 125 with 1 here. And I get 3/5 to the y power equals 27 over 125. And that seems to be okay. Because I can raise 3 to the 3rd power to get 27. And 5 to the 3rd power to get 125. It's the same one. Let me kind of rewrite them as matching bases to remind you of what it is that we're looking at. This is here, and 27 is 3 cubed, and 125 is 5 cubed, like that. Matching base, set the exponents equal, y equals 3. We done. We are done. Number 20. Oh, I forgot these kinds of problems are on here, and it looks like 22 has it as well. Number 20. 5 to, you know, I take it back. Maybe some of the harder problems are later. I'm thinking of the notes I did with my students maybe and forgetting these are a little different. All right. Number 20. 5 to the 2x equals 1 over 25. I know what to do. I'm trying to think of how to best teach it and talk about it here. Focus. Okay. the exponent terms by itself. That's good. Now it's all about matching bases. Now, you may know what to do based on this appearance alone, but let's dive one step before that. 25 is 5 squared. We know that, but it's in the denominator still. I could rewrite this as 5 squared to get the idea of it, the idea of matching bases, but the bases do not match yet because that base is not in the numerator like the other one is. This goes to a property. It's a multifold property, but the property that if you raise something to a negative exponent, that's the same thing as turning it positive in the denominator. Same as division. Negative exponents mean division. You could also work the other way. If I have a positive exponent, I could turn it negative in the numerator as well. 1 over, follow me here. 1 over 5 to the second power. If x is 5, then I can put a 5 right here. If m is 2, negative m is negative 2. 1 over 5 squared is 5 to the negative second power, and that's what this is here. This is 5 to the negative second power. 5 to the 2x equals 5 to the negative second. Negative exponents do not mean negative numbers. They mean division. So anytime you see a fraction on this side, when that's not a fraction, start expecting negative numbers or do what I did. Work it out. Set the exponents equal. 2x equals negative 2. Divide by 2. You get x equals negative 1. I am done. And that totally makes sense with respect to the property. 2 times negative 1 is negative 2. 5 to the negative second power is 1 over 5 squared, which is 1 over 25. We literally did work backwards on that. Number 21. 2 to the 4x minus 12 plus 9 equals 10. This 9's got to go. Even though there's a big expression there, we'll just deal with it when we get to the final part. I don't think it's going to make it any harder. But we got to do 10 minus 9, and that's 1. And you might be saying, Mr. Robinson, what's so beautiful and great about that? This won't be in the power table either. I think you just got to know what this thing is. Another property to throw into the mix. I've said it out loud a couple times. Any value to the 0 power is 1. With the exception of 0 to the 0 power, but we're not doing it. We're trying to figure out what power I can raise 2 to get 1, right? It's all about matching bases. This is the one with the exponent in it, so let's keep this as a 2, and let's raise this as 2, or let's turn 1 into 2 to what power? The 0 power. 2 to the 0 power is 1, just like anything else would be here. That is the rewrite. Same bases now. We can actually set the exponents equal to each other to make this work. I'm going to add 12 to both sides and divide both sides by 4. I get x equals 3. Okay. 3 more problems to do. We might have hit the all kinds of problems that we'd have. Let's keep working here. 1 over 256 equals 4 to the x. Looks a lot like this kind of problem here. Really, it just does. Fraction when this is not a fraction. So what's going on? 256 is 4 to the 4th power. 256 is 4 to the 4th power. So let's get that rewrite on. So that's 1 over 4 to the 4th equals 4 to the 4 to the x. To get a proper matching base here, this needs to become 4 to the negative 4th power. That's why it was positive in the denominator. Looks like x will equal negative 4. Once you got those bases matched, you feel pretty good about that. That's just how it works. 2 more. 16 to the 3k equals 64. Again, we've seen problems like this. If you check the power table, the only 16 I have on here, I do have 16. 16 squared is 256. 64 is obviously smaller than that. So I'll go back to the power table, but I gotta find a smaller value that I can raise both of these things to get it. 8 is not among them. I can't raise 8 to a power to get 16, not a whole number at least. So check this out. You have 2 different options. You have 4, which I recommend. 4, because 4 squared is 16 and 4 cubed is 64. Or 2. 2 to the 4th is 16. 2 to the 6th is 64. You could actually do either 2 or 4, and it would actually work. Let me show you both of them. Let's do it with the change of base of 4, the one that I would actually probably prefer. Turn 16 into 4 squared. Remember, this is still raised to the 3k power. And turn 64 into 4 cubed. I don't need parentheses because that's all that's there. Let's multiply the 2 with the 3k. They're going to multiply. 2 times 3k is 6k. Like that. Now you have matching bases. Set the exponents equal to each other. Divide both sides by 6. 3/6 reduces to 1/2. That would be the answer. However, let's do this in purple and do it the same thing using 2. Nothing wrong with using 2. You just have slightly bigger numbers. 16 is 2 to the 4th power. There's still 3k. 64 is 2 to the 6th power. Now I got to multiply the 4 with 3k instead of 2 with 3k, and this is a 6 instead of 3. Everything's just twice as big. And while the 2 is kind of half the size. 4 times 3k is 12k. And here I have 2 to the 6. Bases match. Let's set the exponents equal to each other. 12k equals 6. And then you divide both sides by 12 to solve. 6/12 also reduces to 1/2. That's the final answer. So either of them worked. You actually got to kind of choose there. And the last problem of this set, as we cracked the half-hour mark 5 minutes ago, let's solve for A. It's buried by multiplying by 3. 10 is raised into that power, times 3 and minus 7. 2 steps to get this thing by itself. Let's start by adding the 7 over to both sides, like so. And we get 3 times 10 to the 3a. Remember, you can't multiply those. Equals 3,000. I love you, 3,000. Divide both sides by 3. 3,000 divided by 3 is 1,000. And 10 to what power is 1,000? 3 zeros, 10 to the 3rd. 10 to the 3a equals 10 cubed. So I can now set the exponents equal to each other. 3a equals 3. Therefore, a equals 1. That's it. All right, guys, that's solving exponential equations. That hit a couple of the different ones, right? We talked about changing both bases. We talked about the 0 exponent, the negative exponent, multiple steps before getting it by itself, using algebra afterward in the process, working with fractions in the base itself or outside of it to multiply by reciprocals, matching bases with kind of weird algebra things, even an all real numbers answer. I think we hit a pretty good widespread, something an integrated Math 1 class would be more than happy to look at. And IM3, it's a good introduction before you do things involving logarithms, because not everything has a rational answer like this. But guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Check the description section down below to revisit any timestamp of any one of the 24 problems that we hit here today. Ask me questions in the comment section, and talk to you later. I will see you in the next one.